Good morning, my name is Karina Zornoza.
I'm Shawnak, Verma.
Valencia.
And my name is Ramos.
And today we'll be presenting Robotic Face to simulate humans undergoing eye surgery. First, we'll go over a brief outline of what we're going to be explaining today for our project. Beginning, we're going to start with the project description, the sponsorship for it, motivation for it, the design alternatives we went through before or after the research, final design concept, the analysis done on this concept, and how it will reach global design accessibility. Robotic technology is being implemented in many medical fields, including ocular care. We were tasked with creating a robotic face with special emphasis on realistic eye movement. The next priority was to make it easily manufacturable so it can be easily accessed all over the world. And eventually we will incorporate mouth and eye movement so that it can create facial expressions. Dr. Austin Buck, the ophthalmologist, and his company, TYP LLC, will be providing a partial budget for this project. Now, eye surgery can be very tedious and tiring, and this is why the doctor has created a prototype of a slit lamp for robotic eye surgery. But before human trials begin, he needs a robotic face that he can simulate this surgery on, which is why he's tasked us with this project. It will be used to append to this robotic slit lamp. Eventually, with the facial features added in the second phase of our project, it can be used for many other applications, including sign language teaching.
Robots have been increasingly used where humans can avoid repetitive or dangerous tasks. That's why they're extensively used in the manufacturing industry. Healthcare, however, has remained relatively untouched by robots. Humanoids, which mimic human expressions, are trying to change that. An early pioneer in this field was Leonardo da Vinci. He made an anthropomorphic device, as you can see on your left, which looked like an armored knight. Notable tasks this could achieve was that it could flex its arms, it could rotate its head, and it could sit up and down. A more current prototype is Kismet, which is MIT's robotic face prototype on your right. A very remarkable thing which this robotic face could achieve was that it could mimic almost every human expression because it had almost the same number of muscles. These are some of the related standards which we will be continuously referencing throughout the manufacturing of this project. Some of them are OSHA, ISO, and IEEE. The team brainstormed and we reached the conclusion that servo motors would be the best actuators for our design, and we narrowed down to two design alternatives. On your left is the first one, the cable tendon system. It has 6 servo motors for the actuation system, 3 servo motors per eye. 2 servo motors control the eyelids, and 1 servo motor will control the eyeball. The eyeball and the servo motor will be connected through a monofilament, which is great and inexpensive. It's a very simple design. It is very compact, and therefore it has a very fast 3D printing time. The second design is a rigid connection design. It also uses 6 servo motors for the actuation system. By rigid connection, I mean the motors and the eyeballs are directly connected. It's a relatively more complex design, and therefore it's not very 3D printing friendly.
So we consider all possible options for the design, and as a group we decided that we're going to go with this prototype. And the reason we're going to go with this prototype is because of these reasons right here. The first one is because it's efficient configuration. This is only made of 3 different parts: the base, the frame, which is going to house the 2 eyes, and the frame on top, which is going to house the 2 servos, which are going to move the eyes. Second, it's fast printing time. We have calculated about 5 hours of printing in HD quality. Also, it's accurate movement with monofilament. Like I said, he mentioned before, monofilament is very accurate when accelerating objects. And also the fast assembly. All of the parts are going to be assembled into the base. They're going to just be mounted on the base, so it's going to be very fast. And it was the lowest cost. This is a material selection for the for the prototype, this is what we have estimated, and these are the main components of the design. The reason we chose this design is because ELA is strong, durable, and mineable. We are going to use a servo SG90. This is a micro servo, and it has a very good torque, rapid acceleration. We also want to control the design remotely. That's what we're going to use a T12Z8 controller, and like I said before, the monofilament is very accurate for this type of applications.
So for the engineering analysis, since we want to accomplish the most accurate results, we came up with the idea to obtain two different types of analysis. One of them is a motion analysis, and the other one is acceleration analysis. And so right now we have our angular displacement analysis for the eyelids. Our prototype will be using a 4-bar mechanism for the movement of the eyelids. These are two examples of a daily base uses of the 4-bar linkages, and this is our actual prototype. For the formulas, we decided we need to focus on position, velocity, and acceleration in order to accomplish the most accurate results. For simulations and SolidWorks, we decided to input the same values. We tested our prototype between 200 and 400 hertz, and we were trying to accomplish 14 degrees of closure between the eyelids. The actual results that we obtained were, for the upper lid, we obtained 14 degrees of closure, and for the lower lid, we obtained 104 degrees. It is good to keep in mind that we established 90 degrees as a fully closed eye. This is the actual simulation of our prototype, and this is the graph of our angular displacement of the eyelids. For future work, we're going to continue our engineering analysis. Since we just started it, we need to accomplish acceleration and moving of the eyeballs. Next, we're going to start obtaining materials and parts so we can start our manufacturing process. Later on, we're looking into adding mouth, cheeks, and eyebrows to the prototype so we can implement the sign language into our prototype. For global design, since our prototype is meant to be a training tool for ophthalmologists around the world, in case needed, our team is able to provide a user manual in 3 different languages, which are Spanish, English, and Hindi. As we said earlier, our prototype will be also 3D printed, which will make our manufacturing costs really inexpensive, and our material selection will be widely available around the world. As we all know, eye surgery is a global concern, so our prototype will be globally in need.
This is a Gantt chart showing the projected timeline of our project. We've already started on the analysis. Next, we will move on to the manufacturing, the testing, and the validating for our project. To summarize, we were tasked with creating a robotic face to create realistic eye movement on it. We've already chosen a final conceptual design. Eventually, next semester, we will show you a final prototype, which has been manufactured and tested. Thank you. Yep.
When you're talking about eye surgery, what exactly are we talking about?
More cataract surgery, glaucoma surgery, more specialized surgeries like that, not basic.
Okay, so normally when a doctor is doing those kind of surgeries, and I should know because I had both my eyes done, they normally immobilize the eye. They immobilize the muscle behind the eye so that the eye doesn't move. So my question to you is, why are you introducing eye movement in the face?
I think we can. So there's different types of surgeries. For example, laser surgery, when you correct the angle of the retina, sometimes they numb the surface of the eye, right? But you are able to move the eye as well in that matter. So what we want to accomplish in this design is we want to simulate realistic movements in the eye when the laser is actually targeting the point where you want to want to fix, when you want to like sort with that. So that's what we want to achieve: small movements and accelerations of the eye when it's moving.
So just to more, I guess to answer more your question will be like it will depend on the eye surgery that's been implemented into the project, into the prototype. There will be surgeries where we don't need any eye movement, so our eyeballs won't move, and there will be other eye surgery which the eye will be required to move, so we will move it.
Who gave you the requirement that the eye only moves in one direction? Because you're using one motor per eye, right? You said 2 motors for the eyelids and then 1 motor for each eye.
We're using 6 different servos. So 4 of them. So 2 of them are going to move the upper and the lower lid of one eye, and the other 2 are going to move the other one. And then the other 2 that are going to be mounted on top. One is going to move 1 degree of freedom of the 2 eyes, the up and down, and the other one is going to move the left and right.
How are you going to determine the motions that you're actually going to design around, your design inputs?
So that's a good question. So we have videos from actual surgeries, so we can determine the amount of movement that will make on that, and then we will determine the error percentage that we want to achieve on that. So we have calculated about 10% of error in that.
And why do you need to do 2 eyes?
Because that's
They only do procedure on 1 eye at a time.
right. But this is not only going to be used. The future uses for this is not only for eye surgery, but we want to do sign language as well. So we want to teach, maybe sign language with the prototype as well.
On top of that, we're stimulating the human face as closely as possible. So, like, I guess even if the surgery is 1 eye at a time, the more closer it looks to the actual situation, the better it is.
So wouldn't it be easier to just perfect one and then copy it over instead of working on both of them at the same time?
There's a question. The 2 eyes are going to be they're going to move at the same time in the same rate and in the same acceleration. So it's just to make it realistic. That's why we want to make it.
But is that realistic?
Yeah, it's not. Your eyes don't move at the same time in the same direction.
Well, we have to then sure about that.
That will be more into our analysis. We just started doing the analysis part. We need to do more research on how the eyes are actually moving and then implement it into our simulation.
How do you plan on using that video as an input for your system?
We're gonna get more data from the doctor, because that we want to go over the parameters that he established from his actual surgeries.
Also, a good idea that we can implement is when we're programming the robot. Normally, when you point something at him, your eye is gonna follow the object. So we can also implement that into a robotic face. If, for example, the doctor's gonna be in front of you holding something, it is the tendency that you're gonna try to follow that object. And that will generate eye movement. We can also implement that into a robotic face.
For that, you need motion sensors, and now you're getting a little bit more complicated.
That's actually something that we want to achieve in the maybe next phase. Right now, we actually focus on the actuation system, because we want to make it realistic first, and then we want to do more testing on how we make the robot actual, realistic with sensors, like you said.
So, going back to the question about the mobilizing the eye, same thing happens with your eyelids. They're usually clamped open to prevent you from blinking or from involuntary movement. So, sort of going by the 2 comments, it seems that for this particular application, you're putting a lot of work into areas of the design that are not going to be used for this particular issue. You might see it. I know you said you want to use it for sign language, and that's great. But your primary focus is robotic or eye surgery, and it seems that a lot of your time is being spent designing features that are not being used for the primary purpose of this project. So, I mean, have you thought of just using this approach, but for sign language rather than for eye surgery? Just changing your scope?
Right. If you think, when it comes to the mechanism that we're using to move the actual eyelids and the eye, there's no difference. We're using the same mechanism. We're using a 4-bar mechanism to analyze and perform different simulations. So it's not, we're not really focusing on the eyelids, or it's just the same mechanism for all of them. And that's how we want to achieve the precision of the actual prototype.
That's fine, but when you're testing this, you're trying to make it as human-like as possible.
Right.
So when you put this robot under the eye doctor, the surgeon, and they follow the same procedure, they would numb the eye, they would clamp open the eyelids, and from just doing that in your procedure, you rendered all your 6 servos useless. So it's really just a mannequin sitting there that you won't be able to move. So my question is, have you considered just following the same design that you have, just its application being different? Moving away from the eye procedure, or targeting the eye procedure but without the servos, but making your primary focus the sign language.
No, we wanna pursue that's our main goal is to make it realistic, and also remember the prototype is to train the ophthalmologist. So they wanna use this prototype to test the actual machine they're gonna use to perform eye surgery. So what they wanna see with this prototype is what can go wrong with it, right? So that's why we have the eyelids, the movement, because like you said, sometimes it doesn't move. But if it does, what can you correct from that?
What's the cost of this project? You mentioned that it's being partially covered by the doctor.
We actually put that on the previous slide.
Thank you.
Any other questions?